Hello everyone, welcome back. Let's talk about another medium problem on Leetcode today. Letter tile possibilities, Leetcode 1079. If you are new to the channel, consider subscribing. I try to make daily videos on the problems related to data structures and algorithm, including detailed explanations, optimized solutions, and step-by-step walkthroughs to help you improve your coding skills. Now to the problem. In this problem, we are given n tiles, where each tile is represented by a single letter printed on it. And some tiles may have duplicates as well, for example string AAB here, and we have to return the number of possible non-empty sequences of letters that we can make using the letters printed on those tiles. Then in example 1, we have total of 8 unique sequences, 2 unique sequences of length 1 which are A and B, 3 two-letter sequences which are AA, AB and BA, and 3 three-letter sequences which are AAB, ABA and BAA. Hence total of 8 sequences, and that will be our answer. And now in terms of constraints, the length of the tiles is less than equal to 7 and greater than equal to 1, and the tiles consist of only uppercase English letters. Now in terms of solving this problem, we need to count the permutations that can be generated using the characters of the given string tiles. To start with, let us consider a simple sequence ABC. If we were to find the permutations of the entire string, that is all the 3 tiles, then it would have been 3 factorial, which is equal to 6. But our task is to find the permutation not just of the full string, but for all sequence lengths k from 1 to n, where n is the total number of tiles. Each sequence length has to be considered separately, and in this string there are no duplicates. We can break the problem into 2 distinct steps. First, we select the tiles, and then we permute the selected tiles. For a sequence of length k, we select k tiles from n available tiles, and this selection can be done in nck ways, which will be equal to n factorial divided by k factorial into n minus k factorial. For example, we can create a subsets of size 1 in 3c1 or 3 ways, which are A, B and C, and subsets of size 2 in 3c2 ways, which will be equal to 3 factorial divided by 2 factorial, which is equal to 3 itself, and those will be AB, AC and BC. And we can create a subset of size 3 in 3c3 ways, which is equal to 1, and the characters will be ABC. And then the next step will be to permute the selected tiles, and that can be done in k factorial ways, where k is the length of number of tiles available to us. For example, here we have only one character each, so each of these subsets will create 1 factorial or 1 permutation each. For these subsets of size 2, we can create 2 factorial permutations each, that is 2 each, like AB to BA, AC to CA, BC to CB. And for ABC, we already saw that the permutations of this string will be 3 factorial, that will be equal to 6. So in this case, we will be generating 3 into 1 factorial plus 3 into 2 factorial plus 1 into 3 factorial sequences, which will be equal to 15 sequences, and that will be our answer. So if we generalize, it will be equal to summation of nck into k factorial, where k can go from 1 to n. But here the string doesn't have any duplicates, so this approach was straightforward, and the formula is efficient for calculating all the permutations. However, the string may contain duplicates. For example, consider the tiles AAB. Here the character A is repeated. Now let us try to understand how the presence of duplicates changes things. When the string has duplicates, say one character occurs n one time, another character occurs n two times, and so on, and we have m distinct characters in the string, then the unique permutations of the string will be equal to sum of all of these frequencies divided by factorial of individual frequencies. So it will be n1 factorial, n2 factorial, all the way up till nm factorial. For example, for this string of length 3, number of permutations of length 3 will be equal to 3 factorial divided by count of a's, that is 2 factorial, and count of b's, that is 1 factorial, which will be equal to 6 by 2 equal to 3. Because if we swap two a's, we will get the same sequence, So to avoid the duplicates, we use this multiset permutation formula. Similarly, if we had sequence of length 2, then we can create the sequence like AA and AB. Now A occurs twice, so number of permutation of this will be 2 factorial divided by 2 factorial, which will be equal to 1, or in this case it will be equal to 2 factorial, that is equal to 2 itself. So this will give us total of 3 permutations. So this was permutation of length 3, this was permutation of length 2, and now let's look at permutations of length 1, that will be A and B, which will give us 2 permutations. So we will get total of 8 sequences from these tiles. And now notice that we are choosing these sets. Like here we are choosing 3 letters, here we are choosing 2 letters, and here we are choosing 1 letter to form a subset. If the characters were unique, this would have been very easy. But here the characters are duplicate, making the process more complex. So we must generate all possible subset of tiles, and then for each subset we calculate the frequency count of its characters and run this multi-set permutation formula for that subset and repeat the subsets of every possible length and sum up the results. Even though this approach is theoretically sound, it becomes computationally expensive due to subset generation, which will take 2 to the power of n minus 1 time for subsets of size n, and then for every subset we calculate the frequency and compute the factorial for both numerator and denominator. So this results in total time complexity of O of 2 to the power of n into n, and given the strings are small in constraint, this solution may be accepted as well. But now the question is, can we solve this problem in simpler way, especially during an interview where time is limited? An efficient and clear approach is critical. So here the answer is yes, we can actually pivot. Instead of generating and processing all subsets as we did using the mathematical approach, we can focus on the direct exploration of sequences. By doing this, we avoid the overhead of generating combinations and recalculating frequency counts multiple times. And this is where backtracking comes into play. Backtracking proves to be a cleaner and more efficient solution as it dynamically avoids duplicate counting and incrementally constructs valid sequences. And now to tackle the duplicates, we can either use sorting or frequency map, because if we use sorting, all the duplicates group and come together, and then we can use a visited array or set to ensure the tiles in the same positions aren't counted twice within the same recursion path and count all the permutations. However, we will be solving this problem today with the frequency map. If you are interested in the sorting based approach, I have also covered in the post linked in the description below. So we will create the frequency map. For example, for tiles AAB, we can create the frequency map with A occurring twice and B occurring once. And now instead of iterating through the original string, we can iterate over the keys in the frequency map directly, because by doing this, firstly, we avoid the duplicates present in the original string, and for counting the permutations, the order of characters don't matter. So we dynamically update and restore the frequency counts during backtracking to simulate choosing and unchoosing tiles. At each step, we count the sequence and continue with the recursion. To explore further, let's see this in action. So we have two characters A and B in the hash map. So we can take two paths. We can take A or B. Now whenever we choose a path, we decrease the frequency of the character we just used in the frequency map. For example, here we chose the path A, and now the frequency of A is reduced from 2 to 1 and the count of B stays 1. But if we go with this path, then we have 2 A's remaining but no B remaining. So this is how we will update the map. And now let's continue with our recursion, say with path A. And we already have a 1 sequence here, which will be A. So we increment our count to 1. The frequency map again has 1A and 1B. So we can again choose A or B. So suppose we chose A. Now we have used both the A's and we still have 1B remaining, and the sequence will be double A. So we increment the sequence count to 2. And from here only 1B is remaining. So the only path we can take is to character B, which will result in the sequence as double AB, and now the sequence count become 3. And now since we have used all the characters in the map, we can backtrack by restoring the character B and then restoring the character A and come to this point. And this time we will choose character B, and now we have one character A remaining and no B remaining, and the sequence will be AB. So we increment the sequence count to 4. From here we don't have any B remaining. Only path we can take is to character A, and we form the sequence ABA and increment the count to 5. And now, since again the hash map is empty, we will backtrack and restore A, B, and A and come to character B. And since we use this B, now we have two A's remaining and we formed a sequence B. So we increment the sequence count to 6. And then we have two A's remaining. So we go down and use the character A to form the permutation BA. Now our sequence count becomes 7 and we only have one A remaining. So we go down and form the sequence BAA and increment the sequence count to 8. And now we have no more characters remaining. So we are now done and hence we will return 8 as our answer. And here is a more elegant depiction of the recursion in case it is useful to you. And note that in this problem, we do not need an explicit base case. The recursion terminates naturally when all the characters in the frequency map are exhausted. And at each step, if the character is available, we decrement its frequency and proceed. If no characters are available, recursion simply ends. Now in terms of time complexity, it will be O of m into m factorial, where m is number of distinct characters in the input sequence. Because for each character, we can choose to include or exclude at every level of recursion. And since we are dealing with permutations, this will be proportional to unique sequences that we will generate, which will be equal to O of m into m factorial. And in terms of space complexity, it will be O of n, mainly coming from the recursion stack. And for storing m distinct characters in frequency map, we will require O of m space. But in this problem, we are given that m is equal to 26. So because of this, the overall space complexity is O of n. Now let's jump into the code part. First, let's create the frequency array of size 26 to store uppercase letters from A to Z. Now let's iterate over each character in the input string tiles and update the frequency for the character using the corresponding character as an index by subtracting the ASCII value of uppercase letter A and increment the frequency count and call the backtrack function, which will return the total number of possible sequences. Now let's define our backtrack function, which will take this frequency map. First, let's initialize the counter. Let's call it total to keep track of total number of valid sequences formed. And now we will start iterating over all the characters in the frequency map and check if the character is still available. If it is, then we will choose the character for the current sequence by decrementing its frequency in the array and increment the valid sequence count. And then we will recursively explore all possible further sequences, including the current character, and backtrack by restoring the frequency of the character in the frequency array so that it can be used for other paths. And in the end, once we are done with all the paths, we will return total as our answer. Now let's submit this code. Cool. So that's all for this video. I hope this video was useful to you. If it was, please give it a thumbs up and share it with others who might benefit from it. If you haven't subscribed the channel yet, make sure to hit the subscribe button and turn on the notification bell so that you never miss an update. Your support helps me create more content like this. If you have any questions or suggestions, feel free to leave them in the comments below. Thanks for watching and see you in the next one.